Thank you. Thank you for inviting me to be here. I'm sorry being late up to the podium. There's a lot of interesting talks here, and I can't stop asking questions about them. So, I'm going to talk about optimal initial conditions and stochastic forcing for central and E-specific ENSO events, and a lot of this talk has been set up very nicely by some of the talks before, so I'll skip through some of the stuff. But this is work that I've done with Matt Newman and Michael Alexander. And the impetus for this was really inspired by some conversations with Cecile Penland, who suggested targeting analysis using specific norms. So quick background here. We've talked about the two modes of variability in the tropical Pacific here, and I'm going to represent the two dominant modes of variability using the first two EOFs, similar to what Kathy did earlier. On the left, we have what I'll refer to as a standard ENSO event, and that's not an indication that there is such a thing as a standard ENSO event. It's just that that's the way that the covariance matrix breaks that down. And on the right, I'm going to represent the Pacific meridional mode as the second EOF of sea surface temperature over the tropical Pacific. And justification of that comes from looking at the time series of those two, the Pacific meridional mode, which is determined via maximum covariance analysis between SST and surface winds. If you take the SST component of that and plot that, that is the blue dashed line in the bottom curve. And if you plot the second principal component of sea surface temperature, then we get the black curve in the bottom plot, and those two are correlated at about 0.9. So I'm going to use the second EOF as the Pacific meridional mode representation. So Takahashi, 2011, took a look at central and E-specific ENSO events in terms of a rotated phase space between the EOF1 and EOF2 directions. And on the right, you see the figure from Takahashi 2011, which shows the E index, the E-specific index, and the C index, the Central Pacific index. And so the Central Pacific index is defined as the sum of the first and the second EOF. And the spatial pattern associated with that is depicted here, and I would we'll call that the Central Pacific event. And then the E index is defined as EOF1 minus EOF2, so, and the spatial pattern associated with that is shown here, and that represents Eastern Pacific ENSO events. And so Takahashi showed that a lot of the commonly used indices for Central and East Pacific ENSO events can be described by these two. So what I'm going to do is take a look at optimal initial conditions that generate Central and East Pacific ENSO events, and we're going to sort of brute force look at these things by imposing a particular norm. So I'm going to use linear inverse modeling. This was described in a lot of talks so far. Assumes a linear approximation to the full system. We can solve the homogeneous equation to obtain a Green's function, and that Green's function can be estimated using the lag covariance statistics of the system. So in this case, we're going to use the leading 9 principal components of tropical Pacific SST from the HADIS data set, and the leading 3 principal components of 20-degree isotherm depth, and that comes from the SOTA reanalysis. So similar to what's been done before. We can alter those the number of PCs in SST, and then we can also add wind. It doesn't change the results particularly. So the difference between what I'm going to show here and some of the other things is that as Antonietta showed, we can define growth of the system based on the norm of a final state of the system divided by the norm of the initial state of the system. And I've expressed this in a very particular way by leaving these subscripts on to indicate that that norm, that growth, is determined based on how we want to measure it. Right? We can look at growth in a particular direction, and in this case, that is represented by this norm kernel n. And that the final norm kernel n. We can also look at growth relative to some specified initial norm kernel L. And in our case, we have I have no reason to specify an initial structure. And so we're going to use the identity matrix for L. But we are going to specify this final norm kernel, N, as being looking at growth in a particular direction, and those particular directions are going to be the Central Pacific or the East Pacific ENSO directions. So growth, we want to grow the numerator with respect to a condition, an arbitrary constraint that we just set the denominator equal to a length of 1. And so we can set up the Lagrange function, differentiate with respect to elements of x, and we end up with the generalized eigenvalue problem here at the bottom. Solving this problem gives us initial conditions P, which optimally grow in the direction that we specify for n, subject to the constraints of L, which are an identity matrix. So what does this actually mean here? So this is what happens when our final norm is the standard L2 norm, just the identity matrix. So we're just growing variance in this case. And the optimal initial condition for the 6-month initial condition gives us this structure, which we've seen quite a bit so far. This warm band here in the subtropics, warming in the eastern Pacific, this band of warm anomalies in the southern subtropics, and then a deeper thermocline in the western and central Pacific, and some sense of maybe a shoaled thermocline in the northwestern tropical Pacific. If we initialize this model with this structure, 6 months later, we get this structure. So the shading here is the sea surface temperature, and the lines are the thermocline depth. And we see something that looks like a mature ENSO event. So the key features here that I'm going to discuss today are this feature 1, 2, and to a certain extent the thermocline features here. So now let's take a look at what happens if we specifically try and grow in the direction of the Central Pacific event. So if we look at optimal initial conditions that lead to a Central Pacific event. When we do that, we end up with this broad warming across the subtropical Pacific here as really standing out in this. So this resembles the Pacific meridional mode quite a bit. And the warming in the eastern Pacific is minimized quite a bit for this particular optimal. And the thermocline structure is really dominant in the western Pacific. So this is very similar to some of the stuff that Kathy showed, as well as Antoniette. And if we let that pattern evolve over 6 months, then we end up with this pattern on the right here, where we see something that looks like a Central Pacific ENSO event. In contrast, if we specifically try and grow in the East Pacific direction, our optimal initial condition looks very different. The Pacific meridional mode is largely gone. And whereas with the Central Pacific event, we did not have warming in the Eastern Pacific as an important precursor. For the East Pacific event, we do have that warming as an important precursor. To a certain extent, we see some warming in the Southern Ocean as well. And I do not yet know how robust that is based on just playing around with the numbers of principal components and so forth. But it does appear here. And then the other thing that appears to be robust is that a deeper thermocline across the Central Pacific is a precursor to the East Pacific ENSO event, as well as shallow thermocline in the off-equatorial Pacific. So putting those two together, these are the two different structures that optimally grow to a Central Pacific versus an East Pacific event, and the major difference here that I would argue is the role of the Pacific meridional mode. And we can quantify that now by, instead of looking at these structures in physical space, we can quantify this by looking at the structures in the reduced space, the principal component space of the model in the first place. So remember that that the second EOF, so what I'm showing now is the amplitude of each one of the modes and their contribution to the optimal structures at given lags. So at lag 0, if you want to grow something with no lag, then you start off with what you're trying to grow, right? So this just recovers the norm itself. Here the blue curve is the Central Pacific norm, the sum of EOF1 plus EOF2. You have to scale that by the eigenvalues, that's why they're not equal to 1. And then the red curve is the East Pacific norm. And as we look down at larger and larger lags, the dominant difference between any one of these optimal conditions is EOF2. It's the second mode, which is the meridional mode. We can further quantify that by looking at the projection of the Central Pacific optimal structure at some lag onto the standard L2 optimal structure at that same lag. And when we do that, we find that that projection for lags of about, 3 to 6 months is somewhere between 0.5 and 0.7. For the East Pacific initial conditions, we get about the same, somewhere between about, I guess maybe 0.7 and 0.8 or so. When we remove the second EOF and recalculate the projections, that jumps quite a bit. And so the dominant difference between our standard optimal structure and the Central Pacific optimal is EOF2. And in fact, if we just take an average of the East Pacific and the Central Pacific optimal structures and project that onto the L2 optimal, we end up with almost exactly recovering the L2 optimal, which tells us that our standard L2 optimal can be well expressed as a linear combination of the optimal conditions that lead to a Central Pacific and an East Pacific event. We can go one step farther here and ask what structures lead to those optimal initial conditions. And so I'm following a method by Penland and Harton here. Although this needs to be redone with higher frequency sampling here. And so given our assumption that goes into linear universe modeling here, we can estimate the noise forcing based on a residual from a center difference on the state of the system, which gives you the derivative, minus the dynamics here. And so that gives us some estimate of the noise forcing in our PC space. We can project the optimal onto that noise forcing, and what it tells us is a time series of how the noise is forcing a particular optimal. What I'm showing here is the correlation, the regression of sea level pressure onto the noise forcing of the CP optimal, and then underneath it we have the CP optimal. And on the right, I have the regression of sea level pressure onto the noise forcing for the EP optimal. And what we find here is that the structure that leads to the Central Pacific optimal is this North Pacific oscillation. So this is perhaps not surprising given the talks that we've seen so far, but this is a way of directly getting at that using the dynamics of the system. On the right, we don't see the NPO as an initial condition, and that kind of makes sense given that the reduced role of the meridional mode. We do see something here in the southern hemisphere. Again, I'm not, when you divide this up seasonally and when you divide this up into kind of subsets of the principal components, I'm not as convinced of the robustness of this. The seasonality of the NPO really does come out of the, when you tear this apart. So the conclusions here, the use of these norms provides a nice tool for targeting analysis of growth of these Central Pacific and East Pacific ENSO events. And the Pacific meridional mode is an important contributor to the Central Pacific events. It doesn't play much of a role for the East Pacific events. And what I didn't show here, the thermocline variations are critical for the East Pacific events, but you can recover the Central Pacific events without any thermocline coupling to the SST. And in fact, if you did all of this using an SST-only limb, you would also you would also get the same optimal structures, or very similar optimal structures. And last, for the noise forcing, the atmospheric NPO is an important contributor to the Central Pacific events. So, thanks.
I think we can have one question. Yes, back.
You mean the East Pacific pattern?
Yes.
That's a good recommendation. Thanks.
You get Rossby wave propagation
Yep.
that actually either strengthen or weaken the trace.
Yeah, and this is commented in your earlier papers on this and using the Indian Ocean SSTs, I believe, right? Yeah. Thank you.